Okay, so just look around you for a second. That fizzy drink you've got, the air you're breathing right now, you are literally surrounded by one of the most basic things in all of chemistry, solutions. So today, we're going to pull back the curtain on the hidden science of how stuff mixes. And trust me, you're going to see it's happening everywhere, all the time.
I mean, have you ever really thought about your morning coffee? You dump in a spoonful of sugar, give it a quick stir, and poof, it just vanishes. Gone. But where did it go? Seriously. That super simple everyday thing you do without thinking. That's our way in. That's the key to understanding the chemistry of solutions. And spoiler alert, it's not magic, it's science. And it is way cooler than you probably think.
All right, so to really get what's happening in that coffee cup, we've got to learn the lingo. It all boils down to just 3 basic building blocks. Super simple.
Okay, first up, we've got the solute. That's the stuff that gets dissolved. And here's an easy way to remember it. Think of the solute as the guest showing up to a party. So in our coffee scenario, the sugar, that's our guest. That's the solute.
And of course, every guest needs a host, right? Well, in chemistry, that's the solvent. The solvent is the substance that does the dissolving. It's usually the thing you have more of. So the hot water in your coffee mug, that's our host, the solvent, ready to welcome that sugar. So what happens when you put the guest and the host together? Boom, you get a solution. A solution is what we call a homogeneous mixture, which is just a fancy way of saying everything is mixed up perfectly and evenly. The guest and host are mingling, the party's a total success, and you've got your perfectly sweet cup of coffee. Okay, now you're probably thinking, got it. Solutions are just solids dissolving in liquids like sugar and water. And yeah, that's one kind, but the world of mixtures is way, way more surprising than that. I mean, just look at this. A solution can be a gas mixed into another gas. That's literally the air we're all breathing right now. It's mostly oxygen dissolved in nitrogen. Or it can be a gas in a liquid. Hello, that's the fizz in your soda. And get this, you can even have a solid dissolved in another solid. That's how we make metal alloys, for everything from musical instruments to jewelry. It's wild.
And solutions aren't all the same strengths either. They have different levels of concentration. Think of it like a dance floor at a party. An unsaturated solution, that's a party with tons of room to dance. You could easily invite more people, more solute to join in. Now, a saturated solution is when that dance floor is packed. It's at max capacity. No more dancers can squeeze in. And then you have supersaturated. This is a really unstable situation where you've somehow crammed way more dancers onto the floor than should be possible. It's so delicate that one wrong move, and bam, everyone comes crashing out.
Okay, let's circle back to that can of soda for a minute. We know the fizz is just carbon dioxide gas dissolved in the liquid. But how on earth do they get so much gas to stay dissolved in there? Well, the answer is all about pressure.
So what does happen when you try to mix a gas and a liquid? Like I said, the answer is right there in your soda can. It's all explained by a really important rule in chemistry called Henry's law.
Basically, what Henry's law says is that the partial pressure of a gas above a liquid is directly proportional to how much of that gas is dissolved in the liquid. Okay, what does that mean in plain English? It just means the more pressure you put on, the more gas you can force to dissolve. It's a super direct relationship. More pressure, more fizz. It's the secret behind every fizzy drink on the planet.
And of course, there's a formula for it. Now don't get hung up on the math here. Just look at the P, that stands for pressure. The only thing you need to know is that as that P on one side goes up, the amount of gas dissolved in the liquid on the other side goes right up with it. Simple as that.
And this law isn't just for soda. It has some pretty huge real-world consequences. With soft drinks, right, they use super high pressure to force that CO2 in. The moment you crack open the can, shh, the pressure is released and all that gas comes bubbling out. But think about deep sea diving. The intense pressure underwater forces more nitrogen to dissolve in a diver's blood. If they surface too quickly, that pressure drops fast and then nitrogen forms bubbles inside their body, which causes an incredibly painful and dangerous condition called the bends. And then there's the total opposite, high altitudes. Up in the mountains, the air pressure is way lower, which means less oxygen can dissolve in your blood. And that's what causes altitude sickness.
Okay, so we've seen how these mixes form. But does that mean it's always perfect? Do all these different molecules just get along when you throw them together? Yeah, as you can probably guess, it's not always one big happy family. And that brings us to the difference between what we call ideal solutions and, well, non-ideal solutions.
An ideal solution? Think of it as a perfectly polite party. The attraction between molecule A and molecule B is exactly the same as the attraction between two A's or two B's. Everyone gets along equally well. So when you mix them, there's no drama. No change in energy, no change in volume. But let's be real. In the real world, most solutions are non-ideal. When you mix them, the new molecules either really like each other and cling together, or they kind of repel each other. And that can cause the solution to release or absorb energy and even change its total volume in some pretty weird ways.
And these graphs right here show us exactly what that looks like. On the left, that's called positive deviation. This happens when the molecules, once they're mixed, don't really like each other. They're trying to get away from each other, so they escape into a vapor more easily. And that makes the vapor pressure higher than you'd expect. Then on the right, you've got negative deviation. This is the opposite. The mixed molecules are super attracted to each other. They're holding on for dear life, which makes it harder for them to escape. And what does that do? It lowers the total vapor pressure. All right, for our last section, we're getting into something that honestly feels a little bit like magic. Did you know that by just dissolving something into a liquid, you can give that liquid brand new abilities, almost like superpowers? No joke. These are called colligative properties.
Okay, now here is the absolute key to understanding this. Colligative properties do not care what you dissolve. It could be sugar, it could be salt, it doesn't matter. All they care about is how many particles you dissolve. It's all about the number of guest particles you add to the party. It is literally quantity over quality.
And one of the coolest examples is something called freezing point depression. When you add a solute, any solute, to a pure liquid, the temperature at which it freezes actually goes down. It gets colder. So, why? Well, it's pretty simple actually. The new solute particles just get in the way. They physically block the solvent molecules from lining up neatly and forming that rigid frozen crystal structure.
And this is not just some boring lab experiment. You see this in action all the time. This is exactly why we throw salt on icy roads in the winter. The salt dissolves into that thin layer of water on top of the ice, drops its freezing point, and forces it to melt. Same thing with antifreeze in your car. That stuff lowers the freezing point of the water in your radiator so your engine block doesn't crack on a freezing cold night. Super important, right?
So there you have it.
From the simple act of sweetening your coffee to keeping us safe on icy roads, the science of solutions is just everywhere. It's happening all around us, all the time. It's a pretty powerful reminder that sometimes the world's most complicated phenomena are really just governed by simple mixtures, which really makes you think, doesn't it? What everyday problem out there could you solve with a simple solution?